let us discuss some basics of constraint optimization. The key idea here during this discussion is when we set up the Lagrangian of the function under equality constraints and under inequality constraints, what should be the sign before the constraint equation, right. This is the key question, how should we choose, and the links to this would be in trying to compute the gradients of the objective function and the gradients over the constraint, and then see the relationship between these in terms of the direction that we need to take towards a feasible solution. Though any optimization course can provide you this material, I am trying to cover these basics so that there is continuity in your understanding, and we will discuss these details. Okay. So, what is the motivation? We are interested in minimizing and maximizing functions subject to constraints over the variables. Okay. So, we have an objective function and we are interested in minimizing or maximizing these functions subject to certain constraints on the variables. Some examples where we discuss constraint optimization would be the following: optimize the path from point A to point B subject to traffic conditions, right. Imagine we have a city and there are many roads connecting the city, and there are various objectives when we have to travel from point A to point B. One, maybe I want the shortest path, maybe I want the path that avoids traffic time, etc., etc. So, depending on what I need to solve, I need to optimize over the parameters. A second example could be in the connection to neural networks that we are dealing with. Suppose we want to optimize the square error in the multilayer perceptron subject to a sparsity constraint in the network connectivity across layers. That is, I want to choose synapses that have non-zero or sort of the strength which is significant, right. I want to weed out all the synapses that are lower than a certain threshold, right. This may be another optimization that I could do over the mean square error in a way that I can weed out dead connections or dead neurons. Okay. So, like this we have various examples that we will have to deal with in practice when we have to solve an objective function subject to constraints. Okay. We have to deal with minimizing functions subject to equality and inequality constraints. So, if we think about how this could be formulated in general, f of x is my objective function and x happens to be a real vector in an n dimensional space. I want to minimize this objective function, right. This f of x is the objective function, and this minimization has to be done subject to certain equality and inequality constraints. The equality constraints state that C I of x equals 0, and the inequality constraint can be C I of x is greater than or equal to 0, and I can also make it less than or equal to 0. So, both sides it holds, right. So, I can also have C I of x is less than or equal to 0, right. Both of these cases are possible. And then if you think about one inequality constraint, I can always flip the sign for Ci of x is greater than or equal to 0, and then I can realize an inequality with Ci of x is less than or equal to 0 by flipping the sign, right. Minimizing something is I take a negative and then I can maximize that function. So, one can formulate a set of constraints over which the objective has to be optimized. Okay. A good example is I want to minimize the distance subject to my acceleration constraint, right, that may be a constraint. So, if I have to travel from A to B, I can accelerate, I can decelerate, but if I am subject to a certain acceleration constraint that I cannot go beyond this acceleration limit, then that is a constraint that I am setting up, right. So, this is a very practical situation. Let us discuss further what we can do. Before we begin with the details, let us formulate certain assumptions or terminology. We assume that f and Ci's are smooth and real valued operating on a subset of vectors in an n-dimensional space, real space, right. Why do we want to bring in this smoothness constraint? I mean, if we have to take derivatives and etc. and then investigate, we might want to have this constraint smooth up to a certain point where we need the derivatives to be available to us, and we assume them to be real valued, but in general it need not be, it could be complex valued, but for the purposes of our analysis we assume them to be real valued. Now, f is the objective function as I mentioned earlier, and Ci belongs to the equality or the inequality constraint. Now, we can fuse all the constraints into one set called omega here. So, omega is a set of all vectors x such that Ci of x is 0 and Ci belongs to equality constraints, and Cj of x is greater than or equal to 0 where j belongs to inequality constraint. Okay. So, written compactly, we want to minimize this objective function where x belongs to this set omega, right. This is the overall constraint set. Now, let us go back to our basic calculus. So, if we were to solve an optimization problem in general without any constraints, then the derivative of that objective has to be 0 and del square on f has to be greater than or equal to 0, which is a positive semi definite property. I mean, this is the case when we are looking into a minimization problem, right, just to be very precise. So, we are dealing with a minimization problem. So, therefore, we have to have this positive semi definite property, and in general if del square f at the saddle point x star is greater than 0, then it is a strict inequality constraint and we say it is positive definite, right. So, in the minimization problem, for an optimal solution to exist, these two conditions have to be satisfied. Of course, if you are doing the maximization, this del square f would be less than or equal to 0 and the inequality holds trivially. Okay, so this is what we have from our basic calculus. Now, when we deal with solutions to optimization problems, we can have a local solution or a global solution. So, a good example is the following. Suppose I consider this parabola like this, y equals x square, and I want to figure out the minimum value, because x square is always positive, x can be positive or negative, but x square is always positive, over the real line. X square has a minimum value and that occurs at the point x equals 0, right. So, there is only one solution to this minimization problem, but however I give you a surface which is something like this, then I can have several local minima points depending upon where I am in this valley, right. So, this is the global solution, whereas these other circles that I have are local minima points. The general problem of computing the global optimal global optima or global optimum point is in general difficult. There are no algorithms that can guarantee this, but there are approximation algorithms where we can kind of reach a reasonably good solution within our search space. Now, if you put constraints, for example, let us see what happens here. I take the same parabola y equals x square. I want to minimize over the set of all real numbers, subject to the constraint that mod x is greater than or equal to 2, right. This is my constraint. So, now I am introducing a constraint, mod x is greater than or equal to 2. So, that comprises of these regions that I am shading here in red, where we have to optimize the objective function. So, at x equals to plus 2 and x equals to minus 2, those are the points where this curve has minimum values. There are two solutions as expected, and these solutions are not unique. Okay. But however, without constraint x equals 0 is trivially unique. There are problems when we have to discuss when we have to deal with in optimization, where we may want to bring in some regulatory constraints such that we will end up with a unique solution, and this is another detail when we try to solve optimization problems. So, I think this gives you a sort of idea about the nature of solutions that we get, the local solutions, the global solutions, etc., and subject to constraints. Now, let us see how this problem can be interesting and also non-trivial. Let us consider this problem here. I have this curve f of x, which is this blue curve. Assume it is a parabola or some reasonably well behaved curve, and let us imagine that the red curve here is our constraint equation, right. This is our constraint equation if it is lying on the curve, and it can be a constraint inequality if we bring in something as Ci of x is less than or equal to 0, right. The geometry is important for us here. When we have equality constraints Ci of x equal to 0, then we have to look at points on the curve that are intersecting with the objective function. So, in this case these are these dots that I have here, the black dots, I mean the green dots here. Okay. So, over these points where the curve intersects the objective, it is over these choices that I have to optimize my function f of x. This may not be the case when I look into the inequality constraint. When Ci of x is less than or equal to 0, I am looking into points on the curve that are below this curve here, right. So, it is this region that I am shading. This is how the Ci of x is less than or equal to 0, that is what it means. Now, I am looking into these line segments, here that I am reshading here for your convenience. It is over these points that I have to figure out what is my optimal solution to the objective, right. So, these shaded segments of the curve are regions of interest for us over which we need to optimize the problem at hand. So, clearly as you can see, this is a non-trivial problem. We do not know how this curve is, and I gave you one curve. If instead I have more constraints and more curves, the geometry is going to be over the intersection of all these curves and considering those regions where these curves intersect and then optimize. So, even to get a closed form understanding to how the intersecting regions are, that would be difficult unless we visualize the geometry of the problem. Okay. Let us delve into some basic definitions here. A vector x star is a local solution to problem 1. So, recall problem 1 was minimization of f of x over all x belonging to omega. So, that was our optimization setup. A vector x star is a local solution to problem 1 if x star belongs to omega and there is a neighborhood n of x star such that f of x is greater than or equal to f of x star for all x belonging to n intersection omega. So, here throughout we are looking at this minimization problem, therefore, I am bringing this notion. So, always we assume the minimization throughout our discussion. For the maximization you can always flip the inequality and you can proceed. So, I have a vector x star that is a local solution to my minimization problem, and if x star belongs to omega, right. So, it is a local solution if x star belongs to omega and there is a neighborhood n of x star, that means I consider a small vicinity around x star. So, let us say if this is x star, then my neighborhood can be this region that I am sort of shading in blue. This is my neighborhood, it is a small vicinity. Okay. So, there is this neighborhood of x star such that f of x is greater than or equal to f of x star for every x belonging to the neighborhood that intersects with this with omega, right, which is our constraints. A vector x star is a strict local solution if x star belongs to omega and there is a neighborhood n of x star such that f of x is strictly greater than f of x star for all x belonging to n intersection omega and x not equal to x star. Right, I want to bring in the strict locality. Of course, we know at the point x star we are at minimum. So, if you go away from x star in whichever direction in the neighborhood, your objective would tend to increase, and that is the meaning of f of x is greater than or equal to f of x star. But when we want to bring in the strict notion on the local solution, then f of x has to be strictly greater than f of x star, and therefore x is not equal to x star and x belongs to this neighborhood intersecting the constraint region. There is also another notion of isolated local solution. A point x star is an isolated local solution if x star belongs to this constraint set omega and there is a neighborhood n of x star such that x star is the only minimizer in n intersecting omega. So, a good example is as follows. So, we have a curve here and then possibly we have a constraint, and when we look at this neighborhood intersecting omega, it basically happens to be the only point and that point is the only minimizer. So, that is the meaning of this isolated local solution. Okay. Right, the point is the only minimizer, that is the isolated property here for the local solution. Now, as I discussed earlier, we want to bring in the smoothness constraint of the objective functions and also the constraints, so that we can help algorithms to make better choices during gradient search techniques towards the solution. Right, because I need to figure out the gradient of the constraint and gradient of the objective, and in the process of finding the gradient of the constraint, I land up into problems where I do not have derivatives well defined. Then my search directions can be difficult, right, and therefore to make proper choices it is better to have constraints that are smooth, but in practice we may not be able to guarantee such a smooth constraint, which in case we will have to kind of deal with these and tackle these problems appropriately by defining the derivatives also carefully over regions of interest for us where the constraints where we can take derivatives of the constraints. Okay. There is also this notion of active and inactive constraints. So, at a feasible point x, the inequality constraint Ci belonging to I, capital I, where I is this inequality constraint, is active if Ci of x is equal to 0 and inactive if Ci of x is greater than 0. For example, to think about this, imagine our constraint is this circle and all points that are lying on the circle or inside the circle, right. This is my constraint for example. So, the strict inequality constraint, right, if I have C I of x is so let us imagine in this example maybe I flip this up to have C I of x to be greater than or equal to 0, right. I have points which are lying on the circle or beyond the circle, and I will indicate it with these blue shaded lines. So, it is active if it is lying on the circle and it is inactive if it is outside, strictly outside the circle. That is the meaning of active and inactive constraints. So, this illustration will help us. Now, let us consider an example here that can help us understand the problem.